What is up, Flutter devs? In the previous video, we rendered some Perlin noise using Flutter Processing and the fast noise package, Dart package. Today, we are going to actually implement the processing APIs that generate Perlin noise so that other developers can use Perlin noise without needing to bring in the package and do it themselves. Let's go get into it. Here's where we left off last time. So just in case you didn't catch that video, this is what we painted to the screen. This is three-dimensional Perlin noise. It's two dimensions that change over time. Time is what we're using for the third dimension, essentially. We don't need to add any new functionality compared to this Perlin noise. We just need to make it so that the standard processing APIs for Perlin noise are supported. So let's go take a look. First, there is this noise function, and noise actually means Perlin noise. Random, the random function is used for random noise. The noise function is used specifically for Perlin noise. And you can pass in an X value, XY, or XYZ. You can do one-dimensional, two-dimensional, or three-dimensional Perlin noise. But there are two other methods that we need to care about. noiseSeed. So all noise is random, and all computer-generated random values begin with some kind of seed value. And when that seed value is the same, the series of random numbers are the same. Same thing with the normal random number generator. So there's also a noiseSeed. There's a random seed. There's also a noiseSeed. We need to implement that. And then there's noiseDetail. These are specifically Perlin noise-based controls. Let's see here where they're mentioned. LOD, I'm sure, stands for level of detail, and fall off means how quickly can you go from a high point to a low point or a low point to a high point, that kind of thing. Level of detail is actually refers to what Perlin noise calls octaves. And it's octaves because fundamentally Perlin noise is based on waves. Waves of different frequencies and multiple waves put together. Octaves deal with waves. So the more octaves you use, the more wave detail you tend to get. And the fewer octaves you use, the less detail. That's why it's LOD, level of detail. Fall off refers to what Perlin noise calls gain. Now in this case, processing is referring to fall off as the Perlin noise term. So you might find these two terms used interchangeably when you're talking about Perlin noise, but fall off and gain are the same thing. We need to implement these three methods. We'll come back here to the source code. In the core implementation, here's our existing random stuff. So I just told you a moment ago, we have random seed because random has a seed value as well. And we have the existing random method, which uses the typical pseudo-random number generator that all computers have. We're going to append to this section. And we're going to need, again, three methods. We want noiseSeed, which is going to take in an integer, which is the seed. It's nullable because if you want to return to, let's say, the standard seed, then you pass null, and you're saying like, I no longer care about the seed. You're undoing the setting of the seed. And then we have noiseDetail, which is going to take, let's see here. noiseDetail is going to take octaves, and it's going to take fall off. Those are optional because because you shouldn't have to set both of them at the same time. Maybe you just want to set octaves or you just want to set fall off. If you call it with no values, then it's not going to make any changes at all. But then there's no point in doing that. And then we want the important function, which is noise. And noise, we're going to require at least an X value. We're going to have an optional Y value, an optional Z. Now, I'm not making these optional in terms of the type system. They're optional in the sense that if you don't pass them, we're just going to use a value of 0. And that doesn't make any, like using 0 is fine. We don't need to necessarily call a different Perlin noise function based on what's being passed in. Although for performance reasons, it might make sense to use one method for Perlin 2 and a different method for Perlin 3. We'll come back to that in just a moment. But the point is, from the developer's perspective, the developer can request essentially one-dimensional, two-dimensional, or three-dimensional Perlin noise, and this is going to return a double between -1 and +1. Now, to support those three methods here in core, we're going to create some properties. So first, if we look into the package that we're using, we're going to find out that the standard seed is set to this programmer number of 1337, which essentially spells out leet. The value doesn't matter. I'm setting it here to match what's in the package. There always has to be some kind of seed value, so this one is functioning as our standard default seed value. In addition to the seed value, we need the octaves. The default for processing is 4 octaves, which is stated right here. By default, noise is computed over 4 octaves, with each octave contributing exactly half its predecessor, which means a fall off of 50% or 0.5. Which leads to the next property, which is Perlin noise fall off, which is going to equal 0.5 or 50%. Those are defaults, they can be changed. Now, in both noiseSeed and noiseDetail, we need the ability to recreate the Perlin noise object because, I guess I forgot to put this up here, there's also the actual Perlin noise object from the package that we're using. In noiseSeed, we're going to set noiseSeed equal to seed or the standard default value. And then we need to reinitialize Perlin noise. Down here in the noiseDetail, similarly, we're going to say Perlin noise octave equals the passed in octaves, or if it wasn't provided, we're going to go back to the default of 4. And then first of all, let me come and change this to an integer. And then Perlin noise fall off is going to be equal to the new value, or if it's not provided, we're going to go back to the default value. And then here again, we need to reinitialize Perlin noise. Down here in the noise method, we need to say if Perlin noise is null, then again, we need to initialize Perlin noise. And then once it's initialized, we're going, let's say, I don't know if there's a performance difference between 2D and 3D noise. Let's just always return 3D noise until we find out if that's a problem. Perlin noise, let's see, get Perlin 3 X, Y, Z. Now, I said before that the fact that Y and Z default to 0 doesn't matter, because you're only going to call this method if you're calling it over and over and over again to get a bunch of related values, right? Whether it's in 1 dimension or 2 dimensions or 3 dimensions, the point is that you call noise over and over and over again. Well, if Y and Z are 0 over and over and over again, then they don't impact the result. So it's like all we're really setting here is the initial value for Y and Z. And then the only thing that really matters in Perlin noise is how X, Y, and Z change over time when you pass in new values. If someone only passes in X, then Y and Z are always 0, and it doesn't impact the noise that we're returning. All 3 of these require the initialization of Perlin noise. I put the to-do in there so we could see that it's the same 3 times, which means it's a good time to break out a private method. So we will create a method called initialize Perlin noise, and it's going to set the local Perlin noise equal to a new Perlin noise object with the number of octaves we want. And this package refers to fall off as gain. So we will pass in the fall off, and we will pass in the seed. What did I call that? I just called it noiseSeed. I guess let's be specific. And then what was this? Oh, because I renamed it. Okay. Then we can say initialize Perlin noise. And down here we can say initialize Perlin noise. And then we can say initialize Perlin noise. And in theory, we've now implemented all three of the standard processing APIs for Perlin noise. Now, I still haven't figured out in the testing system how to test behaviors where we paint individual pixels. This goes back to earlier videos where we talk about the difficulties of bitmap rendering with Flutter. What we can do is we can come back here to our prototype, which is still sitting here rendering this thing. And instead of using the package directly, the fast noise package, we can just use normal processing. Therefore, let's get rid of this call here, which uses the Perlin noise object, and let's get rid of the Perlin noise object, make sure everything else is the same. Okay, so all the rest of the code here is just standard looping through pixels and updating pixels. What we will call is we will say S for the sketch.noise. There's a default seed, there's a default detail. All we need to do is pass in X, Y, Z, and we should get a similar, if not identical, result. So this is what it was. Let me shrink that so we can kind of see if it changes too much. All right, 1, 2, 3, save. Okay, so we did have a change. The resolution went way down for some reason. Well, one thing is that I think I wasn't paying attention to what I just deleted, but I think I was messing with the frequency. That's going to be one thing. But we shouldn't be so zoomed in, I don't think. Oh, okay. I was playing off camera before the video, and I increased the frequency and decreased the increment. So I can't remember what we had this as before. Maybe like 5, or maybe this was like 2 and 2, and then Z was 5. Let's save that. All right, now we're back to what we expect. Same result. Like we were already painting this, but now we're painting it using standard processing APIs implemented in Flutter. Now, once I merge this in, all developers using the Flutter processing package will have the ability to call noise, and they will get this result if they want it. That part of noise is done. There's still, so we have random seed, we have noiseSeed, noiseDetail. There's still one more noise method or random method for us to implement from processing, and that is, I think, random Gaussian. So Gaussian noise is another type of noise. That's the third and final type of noise that processing supports out of the box. So in the next video, we will implement that form of noise, and then we're fully complete with the random section of the processing APIs. I'll see you then.